Welcome to the live session. Refraction of light at curved surfaces, teaching class number 4. In the last class, yesterday's class, I discussed with you about applications of curved surface formula, or how to use that curved surface formula for plane surfaces. So discussed in 3 examples. Then now the topic is simply about lenses. So what is a lens actually? What is a lens? So here, what is lens means simply it is made up of a transparent material, and simply it is bounded by two spherical or curved surfaces, bounded by two curved surfaces at least. So here, if you take a glass which we use in the windows or making of mirrors transparent, that also has same two surfaces. If you observe, it has two surfaces, but the two surfaces are also plane here. Can we call this as a lens, sir? No, because the condition is not satisfied. Here actually it is made up of transparent. It is made up of transparent, but here bounded by two surfaces. Okay, it is also satisfying. But now at least one of the surface must be curved surface. Then only it is called as a lens. It is not a lens, it is called as glass slide. So here, what are lenses? Simply made up of two curved surfaces, used a material, transparent material medium, and one must be curved surface. Then it is called as simply a lens. Then what happens to the light? What happens to the light? That light rays, when propagating through the transparent material medium, that which bounded by two curved surfaces. So what happens to the light ray when a transparent material with two curved surfaces is placed in the path of light ray? So before learning about that behavior of light rays, we have to learn about a lens first. So lens definition is given you, made up of a transparent material bounded by two surfaces. One must at least a curved surface. At least one surface must be a curved surface. So here, now we are learning about types of lenses first. What are the types of lenses here? What are the types of lenses here? So here, simply, what are lenses here? What are lenses here? Lenses are simply made by transparent material medium and having two surfaces. So here, depending on the surface nature, I am classifying the lenses into different types. So here, look at, suppose I am using one of the surface of a transparent material medium is here, simply straight, plane. So what this is? A plane surface. So here simply I can call this in the combination as plane, right? So I'll tell you. So here, then the next surface I am using here, made up of a convex surface, bulged out surface. So what the right side surface is? Convex. So here, together, one is plane surface and the other is curved surface. That curved surface specially convex surface. Then the type of lens named as here plano-convex lens. Plano-convex lens. So simple to name this lens type. So how we named? Based on the two lens surfaces. That two surfaces of the lens. So one is plane and the other is convex. So together called as plano-convex lens. Plano-convex lens. Now I'm using the same plane surface. One of the surface is plane surface. Okay. Then now simply here one side plane and another side now assuming concave surface. So what the right side surface is? It is a concave surface. So now it is plano-concave. So here bounded by one of the surface is plane and the other surface is concave. So this type of lens are called as plano-concave lens. Plano-concave lens. Why? One is plane surface and the other is concave surface named as plano-concave lens. Simple to name these lenses actually. Here based on two surfaces that only assigned as name for the lens. So then next, one of the plane combination completed with convex surface and concave surface. Now here I am taking left side as concave surface. So one of the surface bounded by concave surface. Right side also I will take same concave surface. So left surface is concave, right surface also a concave surface. Left surface is concave and right surface is also a concave surface. So here simply two there, left and right, both are concave and bounded by two concave surfaces. So two named as here by or double. So here simply I can assign a code to assign the number of two surfaces, right? So I is by. So by 2. Both are what? Concave. So biconcave lens. So this will be now called as biconcave lens. After this, we have one more type of lens bounded by two convex surfaces. So left side surface is a convex surface. Then right side surface is also a convex surface. Then here both two surfaces are convex surfaces. So here to assign that number, I'm using a code by. Also you can name it as double, no problem, right? So by convex lens. So we learned four types of lenses. What they are? Plano-convex lens, plano-concave lens, biconvex lens, and a biconcave lens. Okay, order missing. Biconcave lens and a biconvex lens. So four lenses we are completed. Are there any other possibility? Combination of two different surfaces. Here plano-convex completed, plano-concave completed. Okay, so plane completed. Two planes, not possible because it is not called as a lens. We can call it as slab, glass slab. Okay, then two concave completed, two convex completed. Then now combination of concave and convex, convex and concave. Now look at that. So here what the left surface is? Concave surface. Here left side surface is concave surface. Then let me take right side surface is opposite. Right side surface is opposite, convex surface. So here one is concave surface and the other is convex surface. So togetherly it is called as or named as concavo convex. Concavo convex lens. Then one more possibility is that left side surface is convex surface. So I'm taking left surface is convex. Then now here that convex surface is now having one more surface as its combination, right side surface is concave surface. So left is convex, right is concave. Then this type of lens is called as convexo-concave lens. Convexo-concave lens it is. So how many types are there? We have namely plano-convex lens, plano-concave lens, biconvex lens, biconcave lens, biconvex lens, concave convex lens, and finally convexo-concave lens. I'm not remembering any lens. Just I am assigning the name of the lens based on its surfaces from left to right. So first left surface and the right surface. So togetherly, I am assigning the name. So this is about the types of lenses. Also, we are able to name that lenses based on the behavior of these lenses. Right? Based on the surfaces, I assign the names plano convex, plano concave, biconcave, biconvex, concavo convex, and convexo concave. Based on the surface. Now, I am assigning the name for that lenses based on its behavior towards light rays. So here in the fourth lesson, to decide a focus, or focal point, we used the behavior of light rays only after refraction. So here, that behavior of light rays considered after the refraction through the lenses. Eyes converging or diverging behavior. Converging or diverging behavior of light rays through the lenses. So here, converging light rays or diverging light rays after the refraction, then they togetherly called as either converging light lenses or diverging lenses. So here, converging of rays by a lens. Converging of rays by a lens is possible or not? Yes, possible. So what is converging of light rays? Actually, that light rays meets at a common point after refracting through a lens. Just look at on the screen here. When the parallel beam of light rays sent passes through a double concave or double convex lens, what happened? They are going to meet each other at a common point. So this common point we can call it as converging point. So this lens is converging the light rays. So based on that type of behavior, here simply the following lenses are called as converging lenses. What they are here? Concavo convex lens, plano convex lens, and double convex lens. So maybe you observed one common thing in the names. Always the right side surface is convex. Always the right side surface is convex. Look at them clearly. Left side concave, right side convex. Left side plane, right side convex. Left side convex, and right side also convex. So simply right side surface is convex. So using this simple word, you can recognize that as a diverging or converging lens. Simple. So right side convex is converging lens. Convex converge. Right side only. Then one more type of behavior. Diverging of light rays by a lens. So how we can diverge? Using a concave lens. So what happens if a parallel beam of light rays focused on the double concave lens? Simple. Observe that light rays all are separated after refraction. So called as diverging behavior. In the backward direction, they can appear to meet, seem to be emanate from the focus. So this is called diverging behavior of light rays. So which lenses are diverging the light rays? So simple. Here, look at the right surface in the both figures. Just look at the right side surface. Here, what the right side surface is? Convex, existing, bulged out, convex surface. What about right side surface? Deep inwards. So cave. So left side, whatever it may be, but right side it has concave. Whatever it may be, the left surface, right side surface is convex. So based on that logic, I am able to classify the lenses as here diverging behavior. So what they are? Here convex, so concave, right side is concave surface. Next, plane and concave, plano concave and double concave. So these are here simply given as diverging lenses. Look at these lenses. Plane concave, convex concave, concave and concave. So names are what? Plano concave lens, convexo concave lens, double concave lens, or given as here simply diverging in its behavior. So called as diverging lenses. So converging lenses 3 and diverging lenses also 3. Totally 6 lenses we have learned. 6 lenses we have learned. Then here the topic is the terminology of lenses. Terminology of lenses. So what the terminology we are dealing in this lesson? Already we learned about the in the previous discussion, I maybe mentioned about a fourth lesson. Already we are discussing fourth lesson. So, sorry, here in this fourth lesson, we are dealing with the lenses, right? So here, lens terminology we have to learn. Lens terminology we have to learn. So for that learning, actually, I said about the lens. What is said to be lens? Having two surfaces, right? One must be a curved surface and made from a transparent material. Transparent material. So here, these are simple characteristics needed to decide the given object as a lens, right? Bounded by two surfaces, one must be a curved surface and a transparent material. So here, simply how you can decide, or sorry, how you can design a lens actually. How you can design a lens actually. So here simply, maybe you have a lens. Maybe you have a lens. Suppose if you imagine this lens as a double convex lens, how do you make this a lens? Simple, I'm showing you here from a sphere. So look at, I'm drawing a sphere here on the screen. Suppose I'll show you it is as a two-dimensional figure only, easy to observe. Then here just I'm cutting this into a part, left surface suppose. So left surface I'm making a part as you see here. So sorry, here maybe you are unable to, I will change the color. Okay, here now look at, just I'm using to cut like this. Just I will bring them very close. Now look at them, what the shape you are able to see here in the middle, white color region. See here it is made as a double concave lens. Double concave lens. Simple. Here, how I made a lens using a transparent sphere. Using a transparent sphere. So that you need to understand what is lens three-dimensionally, right? Assuming three-dimensionally, then here this lens is made up of spherical surfaces, right? So here if you imagine them, that or imagine as a part of, right? So here that right side surface giving you extension like eyes on the screen, then right left side surface as you see here. So two parts, right? So here two arcs you are able to get. I got two arcs, two curvatures. Simply I can call them as two curvatures. So that curvature is what? Is a part of circle two-dimensionally. If it is three-dimensional figure, part of a sphere. So that circle or a sphere both has center from which they made as a part. So here simply the has centers. The has centers. So for that, I am recognizing the centers. So for the first surface, left to right. So this is our first surface here. Then this is our second surface, left to right. So first surface center is right side. Then second surface center is at left side. So that I am giving numbers based on the surface number only. So first surface left side and its center gone right side. So that is given as C1. Then second surface is right side and its center is left side. So that's why it is given as C2. So C1, C2 numbers are assigned. Now I am finding a midpoint in the thickness of lens. Right. So here I will show you with the lines here horizontally and vertically. I am trying to connect them. So vertically, then horizontally, and it's a thickness, maximum thickness where it is available. So I got a point here. So that point I am taking as its a pole. That midpoint, right? Geometrical midpoint of the lens is now given as pole. Also, you can call it as optic center. Polar optic center. Then now the line I am imagining that which is connecting the center of curvature and the optic center. Center of curvature and the optic center. So optic center denoted by the letter P here. Then now the line imagined that which is passing through centers and the optic center. So the line which is passing through center of curvature and the optic center is called as principal axis. That is called as principal axis, or also called as optical axis, So as we learned in the first lesson, the line which is connecting the center and the curvature boundary, that we can call it as radius of curvature, R1. So first surface is R1. For the second surface, we can call it as R2. So how do you draw the normal for the second surface? Simple. The line joining the center of curvature and the boundary at any point. Why, sir, at any point? Actually, in the ray diagrams, we will consider only at the incident light ray. But for showing a normal, at any point you can draw. That line which you drawn from the center to the boundary, that will be perpendicular to the circle, at a given point. So here look at this. That is perpendicular to the normal at a given point. So this is the reason to call that line as a perpendicular or considered to be a normal here only at this point. So don't consider this line as normal at this point. We have to construct one more line by connecting center of curvature and the point you recognized. So any point that connecting the center and the boundary is called as normal. Why? That line what you drawn as a radii of the curvature is perpendicular at that point to the tangential, perpendicular to the tangential line. That tangent means simply the line which can meet the surface only at one point, called a tangent. So you can take this left side distance from center to the boundary is as radius of curvature R2. So we got terms related to the lens. What they are here? Pole, center of curvatures C1 and C2, principal axis or optical center, then radius of curvature R1 and radius of curvature R2. These are explained in the figure number 7 in your textbook. Figure number 7 in the textbook. Now we'll go to the behavior of light rays. What happens if a parallel beam of light rays incident on a convex lens. What happens if parallel beam of light rays incident on a convex lens? So for that, what we need? One lens. So here I am selecting a double convex lens. What the lens is considered here? Double convex lens. Then what to do? Simply identify its terminology. Pole, center of curvatures, right? Then assigning the numbers for them. So left surface is first surface. It's a spherical shape or circular shape towards right side. So that's why C1 is right side for convex lens. Then C2 is left side. Right side surface is second surface. Then it's a center towards left side. So that's why C2 is given left side. Then recognize it's a pole after drawing a line by connecting to center of curvatures. No problem. Then pole identified. Then what to do here? Just we have to instant a parallel beam of light ray. A parallel beam of light ray. So here simply what happens that we have to notice. So how do we observe, sir? Simple. Just naturally in the classroom or in your surroundings, you are able to know about this behavior. How do we, sir? Use one magnifying lens. Magnifying a lens. Simple. Here, just try to focus the sunlight on the paper. Try to focus the sunlight on the paper. So according to first lesson, if source, that means object, and a mirror are separated at a very far distances, that we will consider parallel beam of light rays. From the object, what the light rays we are receiving? Parallel beam of light rays. So eyes for that, simply we are using here sunlight to focus on the lens. That instant light ray on the lens from the sunlight. So sun is very far. So what the light rays we are receiving? Parallel beam of light rays. Okay. So here, when you focus the sunlight on a lens, what happens? What happens? That light you are able to focus on a paper. So you are received actually parallel beam of light rays from the sun. But after refraction, what happens? That all are giving you one bright spot, that image of the sun as a point. So here simply image point you observed. That means all the light rays received only at a one point. That means what? So here that light rays which are passing through the lens deviated from its path and reaching the common point. So according to this observation, what I am doing here, just I am drawing the light rays after the refraction through the double convex lens. So here simply all the light rays are going to meet each other. So already we learned, if a light ray along the principal axis, so what happens? It is nothing but the light ray incident normally, so remains undeviate. So that's why this blue color light ray is given along the principal axis. Then what happens to the other light rays here? They are all going to meet at a common point. Where? On the principal axis. So all the light rays are going to meet each other at a common point, that which is lying on the principal axis. So I obtained a point commonly by these all the refracted light rays. All the refracted light rays commonly giving one point, which is lying on the principal axis. So that converging point, you can call now as here focus or focal point. Focus or focal point. I am giving one number to this, F1, because instant light ray on the first surface So with that, you are obtaining one common point, converging a point of light rays called as focus or focal point, assigned as focal point 1. So that is simply because with the first surface. So here, if you do it from the second surface, you'll get one more point, that is left side to the lens. So that's why I'm given F1. So that's left side point I am recognizing, identifying or designating with a letter F2. So F1, F2. We have two focal points now, right? We have two focal points. Then you are able to measure a length between pole and the focus. So that we can call it as focal length. So simply you can look at this. If a parallel beam of light rays incident on a double convex lens, what we observed, they are all going to meet each other at a common point. So that common point is called as converging point, given as focus or focal point. Converging point of refracted light rays, now called as focal point or focus. Focal point or focus. So here simply you are calling that as here focus or focal point, and given as F1, given as F1 and F2, depending on the surfaces on which surface you are focusing. Okay, then F1 is given. Now another one, you are able to measure the gap, distance, length between pole and focus, P to F1. P to F1. So the length is called as here focal length, denoted by small f. So what is focal length here? What is focal length here? Simply the distance between optic center to the focus. Optic center to the focus. So the distance between optic center and focus is called as focal length. So what happens if a parallel beam of light rays incident or allowed to fall on a double convex lens? All that parallel beam of light rays will meet at a common point after refracting through the double convex lens. So this we observed in this topic. Then same topic, what happens if a parallel beam of light ray incident on a concave lens, on a concave lens, right? So now we will consider, okay, so before that, one more is given in your textbook, that is with the symbol. So for the double convex lens, we can use a symbol here. Double convex lens, we can use a symbol here. What this symbol is given here, double-headed arrow. Why this only selected? Just look at here. If you extend these arrowheads, then try to connect on opposite side, then what you will get? Outline. What you are getting? Simply it is as a double convex surfaces. So this is symbolically representing the double convex lens. So this symbol we can use to indicate a double convex lens. So symbol of double convex lens is double-headed arrow. Double-headed arrow. Then symbols we can recognize that parameters, center of curvatures, C2, C1 or C1, C2 will be same, and identifying a midpoint on the lens surface where they coincides each other, given as pole or optic center, right, denoted by P. Then identifying F1 and F2. So parallel beam of light ray focused on the double convex lens. Then after refraction, what happens? We are going to observe they are all going to meet at a common point. So that common point we are giving as F1 here. So left side to right side F1, then right side to left hand we are giving as F2. So second surface. Okay. So in the ray diagrams, we are always focusing the light on the lens surface from left hand to right hand. Okay, left to right. So here F1, F2 identification is completed. So already we learned about what happens if you focus light rays on the double convex lens. They are all refracting through the double convex lens, and they are going to meet each other at a common point called converging point. So that converging point is recognized as focus or focal point. The length measured between pole and the focus is given as focal length, denoted by small f. Then here simply what happens, now the light is focused on a double concave lens. Light focused on a double concave lens. So here now we can take a double concave lens. So bounded by two concave surfaces. So E is called as double concave lens. Now identify its centers. So first surface, center, left side or right side? Look at that. So spherical shape is giving same side, left side only. So left side we are recognizing as center C1. Then right side, only right side. It's a center also, right side. So C2. C1, left side, C2, right side for the double concave lens. Then identify the points as C1 and C2. Now connect that points, imaginary line that which passes through the center of curvatures and the pole is called as principal axis. Then now what happens if parallel beam of light rays focused on the double concave lens, So here simply they appear to diverge. So here simply what happened here, that light rays are simply diverges. So here in this case we will go in the backward direction, extending the refracted light rays in the backward direction to get a diverging point. So where from they appear to diverge, so that point we will get it by using the backward light rays from the refracted rays. So here I got a common point, that which is obtained on the principal axis. Look at that, the point located on the principal axis. So that is identified now as focus for that. So F1 left side. So do the same process, focusing the parallel beam of light rays from right side. Then what happens? You will get a common point again, diverging point. So that we can give it as F2. So simply if a parallel beam of light rays is focused on the double concave lens, they seem to emanate from a common point called as a diverging point, which is located on the principal axis. So this diverging point of light rays is called a focus or focal point of this double concave lens. Then now you are able to measure the gap length between pole and the focus. So that is denoted by the letter small f. So that is we are calling as focal length. So the distance between the center of curvatures and the focus is now given as simply focus of the concave lens. So here distance and focal point both we learned. Distance and the focal point both we learned. Sir, we have any symbol for this? Yes, we have the symbol for the double concave lens also. Just here look at the shape outline, how you are observing that curved inwards. So see here, that shape only I am assigning here by observing the two surfaces. So here how the shape is, look at that. Here simply that is like this at the top. So one is left side and the other is right side, like this is there. Then here bottom also one is left side and the other is right side, bending like this. So that's why the symbol of the double concave lens we are using here as you see on the screen. Left side curved shape is like this, right side curved shape is like this. So that's why here top surface is used, bottom surface is used like this, then connecting them with a straight line. that the symbol is designed like this for indicating the double concave lens in the ray diagram. So we can use double concave lens shape as you see on the screen. Then now simply go for its centers. So left side we have center C1, right side we have center C2. Then focus, parallel beam of light rays, that which is parallel to the principal axis here. Parallel beam of light rays and parallel to the principal axis. Then what happens that we observed? Appear to diverge from a common point. So after refraction, they are all separated from a common point, appear to be separate from a common point. So that point identified by us, eyes here, simply diverging point. So that diverging point is called as focus or focal point and given with a number F1 symbolically, and number F1 we used. Right side also the same process. Then you will get diverging point number 2 given as F2. So that definitions also given on the screen. Just look at them. If parallel beam of light rays incident on a double concave lens, they seem to emanate from a point on the principal axis after refraction. That diverging point seem to emanate. So that diverging point is called as focus. Then the distance between the optic center and the focus is called as focal length. So denoted by small f. So this lens symbol you can observe how we designed the symbol for ray diagrams based on the outline at the top and at the bottom. So symbolically we are assigning like this. So left you can see is like this. Right also you can see like this. So that symbol is based on the outline shapes. Okay, so this is about a double convex lens and a double concave lens behaviors with the refraction. So simply all the light rays are converging by the double convex lens, that all the parallel beam of light rays appear to diverge, seem to be emanate from a common point. So concave lens is diverging lens, convex lens is converging lens. So we learned about a concave lens and a convex lens symbolically, right? So here we decided the behavior of light rays also. The next topic is to discuss with you about what happens if parallel beam of light rays incident on a double convex lens. That generally here you observed already, but here to decide that behavior of light rays. So here that already given you, that's why you are not going to discuss. Simply we are drawing, right? And we will observe. So that I will discuss with you in the next class. So this class is completed. We will meet in next class. I'll announce the class before I'm going to take. So thank you for joining in the live session. Also give me your valuable comments about my classes. Then if you like, please share with your friends.